Welcome to a course on complex analysis. In this lecture, we are going to see an important concept in complex analysis, that is analytic functions. Analyticity is based upon the concept of complex differentiation, how it evolves, what are the things, that is, what are the definitions that are there under these analytic functions. That is what we are going to explore in this video. As stated, we are going to see about the analytic functions. But before going to analytic functions, I would like to present you about the equivalent form of CR equations. What does this equivalent form mean? In CR equation, we have derived the conditions. That is okay, just a minute. Let me complete it. Yeah. So the CR equation states that what ux equals vy and vx equals minus uy, where your f of z takes the form u of xy plus iota times of v of xy. So the complex valued function is split into real part and imaginary part. Both this real part and imaginary part is treated as the function of two real variables, namely x and y. Okay, we treat the entire complex valued functions as a linear combination of two real valued functions which are defined on R2. We treat that way and we derive these equations, and this is known as the CR equations. With the help of CR equations, we were able to see the necessary and sufficient condition for the differentiability of complex valued functions. Now, what we are going to do is that in the complex form itself, we are going to derive a condition for CR equation, an equivalent form of CR equations, for which what I'm going to do is that is usually we take z as x plus iota times of y, then conjugate of z is x minus iota times of y. So having these notations, we shall write this real part x may be written as z plus z bar upon 2 and y may be written as z minus z bar upon 2 iota. Okay, so now what if you treat some consider a function big f of xy. Okay, so this is a function of consider this function. This is a function of two real variables. Okay, here what we are going to do is that instead of x, we are going to replace this z plus z bar upon 2, and instead of y, we are going to replace z minus z bar upon 2y. Okay, now by chain rule, what we are going to have is that del f upon del z bar. This may be written as del f upon del x, and here f directly involves x and x involves z bar. So del x upon del z bar plus del f upon del y upon del z bar. So here you don't know what this function f is, right? But this is 1 upon 2 plus this is del f upon del y, and this is going to be minus am I right? Yeah, so minus 1 upon 2 iota. So if you take 1 upon 2 outside, then this becomes del f upon del x minus 1 upon I del f upon del y. So when you take a conjugate and multiply on both in the numerator and denominator, then you would get del f upon del x plus iota times of del f upon del y. So from this expression, this f is any arbitrary real valued function, right? So del upon del z, this operator is applied to the function f. This is same as that of half times of del upon del x plus iota del upon del y. This function is applied to the function f. Hence, what we conclude is that del upon del z bar is half times of del upon del x plus iota times of del upon del y. Okay, you may ask me why are we differentiating with respect to z bar? We could have done with respect to z also, right? Yes, you may do it. Okay, do both the ways and see where they lead to. Okay, I am doing only with respect to z bar. Okay, now what we have is that we deduced del upon del z bar is half times of del upon del x plus iota times of del upon del y. So this is what we have deduced. Okay, now we have now let us consider f of z as u of u of xy plus iota times of v of xy. Whatsoever the function is, okay, if you have a real valued function which is defined on R2, then we have applied these things and saw what happened. Now let us apply del upon del z bar to this function f. So it would be del upon del z bar u plus iota times of del upon del z bar v. Okay, so this is del upon del z bar. Okay, this is half times of del upon del x plus iota times of del upon del y. This function is to be applied to u plus iota times of half times of del upon del x plus iota times of del upon del y, and this is to be applied to v. Okay, in both these terms let us take half outside. So it is del upon del x of u is simply what we shall write that as ux plus iota times of uy plus iota times of vx. Iota multiplied with iota becomes minus vy. Okay, let us combine real and imaginary parts. So ux minus vy, this is the real part, plus iota times of uy plus vx, this is the imaginary part. Okay, so we have del f upon del z bar is this one. Okay, now we are going to suppose one thing. Suppose CR equation is satisfied. What is CR equation? That is, okay, so actually this is CR equations we have just written down, and this is where this equivalent form deduction took place. Okay, so CR equation is satisfied. This is our supposition. Therefore, we shall write ux equals vy and vx equals minus uy. So this tells you ux minus vy is 0 and vx plus uy is 0. Therefore, this tells you del f upon del z bar is half times of 0 plus iota times of 0, which is 0. Okay, so this is one way. Now let me do the other way. Suppose del f upon del z bar is 0. So this means half times of ux minus vy plus iota times of uy plus vx is 0. This half is a scalar, so we take it to the other side, so we are left with this quantity. Some complex quantity is 0, which means ux minus vy is 0 and uy plus vx is 0. This tells you your ux must be same as that of vy and your uy must be same as that of minus vx. This is the CR equations, right? So from these two things, what we conclude is that hence the complex equivalent form of CR equation is del f upon del z bar has to be equal to 0. Suppose if you are given some function f is equal to z cube plus z bar, if you are given some equations of this sort, there you don't have to expand it using the notation that z is x plus iota times of y and do the binomial expansion, then look for your partial derivatives with respect to x and then y and look for CR equations. If you are given in that simplest form, just go for the equivalent form. Identify del f upon del z bar. If that quantity is equal to 0, then you are done. It satisfies CR equation. Okay. So, but that does not ensure differentiability as we have seen in the previous lectures. If CR equation is satisfied, then it may turn to be a differentiable function. It will have to satisfy the rest of the conditions as well. But if the CR equation is not satisfied, then we may very well conclude that the function cannot be differentiable. Right? So now we enter into the important concept, that is analytic functions. Until now we have seen enough basics to enter into analytic functions. Now we are actually entering into the concept of analytic function. A function f of c, a function of complex variable, is analytic at z naught if it has a derivative at each point in some neighborhood of z naught. Okay, what they are trying to say, your function has to be differentiable at some point as well as it has to be differentiable at the neighborhood points. Here they are not telling that in all the neighborhoods it has to be differentiable. They are not telling that way. If you are able to identify some neighborhood in which at all points the function is differentiable, then you may conclude that your function is analytic. Okay, so from this what we see is that so from this it follows that if f is analytic at z naught, it must be analytic at each point in the neighborhood of z naught. It must be analytic in each point in some neighborhood of z naught. Actually, if it possesses a derivative at each point of the neighborhood, means at the points in the neighborhood, that same neighborhood can be treated as a neighborhood for all those points that are present in the neighborhood in some way. Okay, this may be, or it may contain a smaller neighborhood than that. So at all those points the function possesses derivative. So if the function possesses derivative in some neighborhood, then we may say it is analytic, right? So that is what we have said. So the next definition, a function Fs analytic in an open set if it has a derivative everywhere in the set. Now I would like to recall a concept that we have seen in the course on real analysis. That is, if a function is said to be open, okay, all those points of the set has to be interior points. By interior point we mean we must be able to identify some neighborhood which is completely contained in the set. Okay, so the sets that are present inside the set, okay, the sets sorry, the neighborhoods are present inside the sets. If you make the union of these neighborhoods, that would form a neighborhood of all those points inside the set itself. Okay, so the entire set can be treated as a neighborhood of all the points on the set. Okay, if the function possesses derivative at all the points of a set, then we simply say the function is analytic in that particular open set. Okay, so now if we have to talk about the analyticity in some non-open set, then we have to consider some open set which contains the given set. Okay, I think I should note it down for your reference. So if analyticity of if analyticity in non-open sets is to be discussed, then we have to consider some open set which contains the given set. Okay, if you are able to produce the analyticity in an open set which contains the given set, then all the subsets of that open set will possess the same property. Okay, that is what we have mentioned here. So next we produce some examples. F of z equals 1 upon z. This is analytic at each non-zero point. In the finite plane. So here by finite plane we mean the complex plane, not the extended complex plane. Okay, so your f of z equals absolute of z square is not analytic at any point, because this function possesses derivative only at the point 0, not even in any point of its neighborhood. Okay, if you take some neighborhood of the point 0, be it very small or be it very large, okay, it does not possess derivative at any of its point, hence it is not analytic at any point. Okay, so next we give a definition of another type of a function, that is an entire function. An entire function is a function that is analytic at each point in the entire finite plane. Which means a function which is differentiable at all the points of the complex plane is called as entire function. So it may also be called as everywhere differentiable function. Okay. So now also we shall produce an example. Okay. The derivative of a polynomial exists everywhere. Thus, every polynomial is an entire function. Okay. Next, we present another definition. If a function f fails to be analytic at a point z0 but is analytic at some point in every neighborhood of z0, then the z0 is called a singular point or singularity of f. Okay. So if we have to produce an example to this sort, z is equal to 0, like, sorry, I'm not able to write it properly. Z is equal to 0 is a singular point of 1 upon z. Okay, so now you may ask me, what about the function f of z equals absolute of z square? It is not. It is analytic only at one point. Sorry, it is differentiable only at one point. Okay, and is not analytic at any point. Therefore, it is not analytic everywhere. So that does not possess any singular point. It must okay. A function which possesses analyticity at some points and fails to be analytic at only very few or countable number of points, there we talk about the singularity. Not to the function which is not analytic everywhere. Okay. So as this lecture goes very lengthy, I stop this lecture now, and the next part of this lecture will be on the theorems and problems on these analytic functions. Thank you.